beyond. Okay, thanks for showing up. As Mauricio said, we're going to be talking about the yet to find oil potential in the pre-salt region of Brazil. We've spoken a lot about this here and elsewhere, showing what the yet to find oil potential is, not just what has already been found. This is an area that we all know, with lots of prospects, fields discovered, blocks under offer. This is more or less a current view. We had a lot of changes in the last few years. A couple years ago was a little less dense with features. Back a couple of years, much less slow. 2013, getting going. And even back in 2009, things were not all very well defined yet, but we can see that the pre-salt is this red line here. This is a artificial human defined boundary. Of course, the geological pre-salt province itself is way different. Nature doesn't obey any of that. But I did want to say that the origins of this work actually go further back. When I did my master's dissertation on the potential of the shallow waters in the Campos Basin, we applied the same methodology. But as I go through this, I got to say, there's a couple, just like in the mafia movies, you can have a kiss on the forehead, taps on the cheek, punch in the face, or a hit in the stomach with a baseball bat. The latter is all of the methodology and so on before we actually get to some of the results. And I think that if you just have a kiss on the forehead, that's just very superficial. You don't get to learn much. Taps on the cheek, you get a little bit more, but you don't get the detail. Punch in the face, maybe you get some methodology, but you don't get the perspective. So we really do want to go through a lot of slides here. I hope you can bear with me, but I think the methodology and the theory behind this is important so we can get a better understanding of what it is that we've done here. First, about the exploratory process itself. There's very basic questions. If the prospect is drilled, we want to know if it's a dry hole or a discovery, if it will be a dry hole or a discovery, and if it's a discovery, how much oil will be discovered. That's what we're in it for. Unfortunately, most of the history of the oil industry, we focus just on whether it's going to be a dry hole or a discovery. We also have to focus on volumes. And in the resource assessment concept, we actually want to know how much is yet to be discovered once we're working on an exploratory area. But the reserve assessment methods depend on the exploratory stage of the area. If it's little explored, we basically have to use subjective methods, indirect methods, and so on. If it's very intensively explored, we actually can use a historical analysis like we've done here. And if we have lots and lots of information, basically you do a volumetric analysis, mass balance. You know everything about the basin, so it's kind of easy just to crunch numbers. But it's basically a deterministic versus probabilistic model approach. It's the deterministic model is basically looking at favorability of the geological parameters. The probabilistic treatment is basically looking at assessment model using stochastic techniques on the information that's historically available. That is a very difficult concept for geologists and geophysicists to grasp, because they're used to looking at actual hard data, rocks, and so on, and we're looking at the big picture when we do a probabilistic analysis. But regardless, obviously the results are only as good as information you have, garbage in, garbage out. So we have to be careful when we look at each analysis, how we go about it. The actual area involved is gigantic, 150,000 kilometers, something square kilometers. So we have to start with some concepts, such as the concept of the area of influence of a well. A single well has an area of influence which exhausts all of the possibility that a field is present around there, because if the field is there, it will have discovered it. That is a concept that back in 77, Schoenemeyer and Drew proposed to model, so that you could gather how the exploration of an area would proceed as you drill holes and you exhaust the possibility that there could be fields that you didn't discover. That is very simple. We go back to their work papers. You can see what they look like. And you represent a field by an elliptical shape, radius A and radius B. So the two radii define a hypothetical field. And then any well here in the center would exhaust an area around here completely, because you can't have a field here without it being discovered. Somewhere between A and B, it exhausts that area partially, and beyond A, of course, the well doesn't tell you anything about fields that can be outside. It's intuitive. You haven't really thought much about it, but that works for the entire exploration area that you're following. So if you have two wells kind of close together, you don't exhaust the area of influence twice. You know, you have an area together here. But if you extrapolate that concept, then you get the concept that large accumulations, large fields, will be discovered very likely first, because they're large, and just randomly, if you stick pins into the exploration area, you're likely to hit the big targets first. And that implies that new discoveries will actually get smaller as you go on in exploration efforts with more wells, because then what will be left over will be the smaller fields. That is also intuitive. We tend to see that. Maybe the exception is when you actually have a different exploration cycle brought about by new information technology, that kind of thing. But in general, that holds. There's a whole concept that's kind of technical, but it's exploratory efficiency, which is based on this C here, which is the exploratory efficiency for a given field size, a class, say, you know, from 10 to 50 million barrels, and another 50 to 200 or whatever. Usually they go double, that kind of thing. The fraction of the discovered fields of a given size class is exactly this formula, where A and B is the area exhausted by all of the wells drilled, and B is the effective area of the exploration region. Values close to C indicate that you actually don't learn too much. You're basically just randomly drilling, and you find new fields basically as you proportional to the number of new wells. That is a case where you're not very intelligent, or you're not very lucky, or all the fields are basically homogeneous in size, so you don't actually have larger fields first. But it's really more efficient to have a C greater than 1. This is what happens when you have a C greater than 1. You do start, this is the axis where you have the fraction of the accumulations discovered. As you start drilling more and more wells, you have greater discoveries, more than proportional to the number of wells. As the exploratory area starts getting exhausted, you basically don't have too much more to discover, so the efforts are less and less effective. If C is 1, you basically learn nothing, and you just go plowing along, and you discover as much as you drill. Very unusual. Most curves are like this, and if you have very good technology, seismic and everything, you're very likely to have a very high C. You discover the good things first, and then later you just work on what's left. Arps and Roberts, and back in '58, studied the Denver-Julesburg basin in the US, lots of wells, lots of discoveries, homogeneous play, and they came up with this correlation between recoverable volumes discovered and the number of wells drilled based on the average area of a discovery for a certain class, and they produce this formula, which also has built in this C here, which is the exploratory efficiency. And again, you have the fraction of all fields of a given size class that are already discovered is this F naught, which is the number of all fields in that size class that exist. You just have to discover them. And the fraction is based on this formula here, where W is the number of wells. And as you drill more wells, you start exhausting it. A is the average area of that size class of field, and B is the total area of the exploratory area that you're working on. So this is very powerful, because now this allows you to predict the total number of fields of a certain size class based on the information that you fit into this formula. This is the part that geologists and geophysicists just don't accept. I mean, they tell you, no, you can't tell me the future just based on that formula. You got to look at the seismic or something. And we say this exploratory efficiency is so powerful that you can't run away from it. This works. And this value would predict the expected return from new additional exploratory efforts. So if you have additional number of wells drilled, you can expect a certain amount of new discoveries. Back in '58, they showed this by plotting the size of the discoveries that were economical, and you see that even small discoveries are not invariably more numerous because they may not be economical. You can have a small discovery that's still economical, but this kind of a shape is very typical. So this is a description that you can then turn into a field size distribution of the sizes of the discoveries, the ones that you make. The ones that you haven't made are probably along the same line. You can plot this in the Lin log. And if you do plot it this way, you get a straight line. And very, maybe not surprisingly, if you think about it, it's intuitive, but this practically any region in the world has a very straight line for a field size distribution. This is how geology works. So when you plot your discoveries along this line, you're basically defining what the line is, and the other fields that exist that you will discover very likely on this line too. This works, they discovered this, and it is used so that when there are sufficient discoveries, the distribution of the accumulation size can be modeled by a log normal curve, and you can use this to do a curve fitting to find a curve that best fits the data available. They did this back then, and they figured it out that if you have a minimum size of viable economical discovery and you have a maximum size, minimum size here and a maximum size here, basically any of these lines can define the exploratory area you're working with. And if you start plotting some along these lines, you discover how your exploratory area will behave with future exploratory efforts. Is basically just figuring out which of these lines you will use. That's very geographic, but you can understand the concept behind this, which is still using the field size distribution to determine what the future sizes that you're going to discover are going to be like. So if you plot a field size distribution curve like this, the actual discoveries, they tend to be very close to what the hypothetical line will be. And indeed, the number of the, cumulative exploratory wells will eventually reach a point where you're not getting too many more discoveries. You get to an area that's mature and you basically give up. At the beginning, you do expect to make significant size discoveries, cumulative discoveries. At any point, say that you're here and you've made, I don't know, 600 exploratory wells, the yet to find oil potential is nothing more than the difference between this ultimate amount of discoveries that you can make and the ones that you've already made. But you can see that to get that yet to find, you have to make a lot more efforts because they're more efficient at the beginning and less so at the end. So here you tend to reach exploratory maturity. A very obvious concept. Examples around the world tend to show this, obviously not perfectly, but you have areas that have come to maturity because additional exploratory efforts just don't add too much to the cumulative amounts discovered. You find that there are cycles in many of these, and these are the cycles that I refer to. People figure out that they understand better the geology, and then they start looking for the discoveries in a slightly more intelligent way, so you can have these jumps here, and this has happened all over the world. But indeed, the concepts of the field size distribution and the discovery sequence that you make underlie the prediction of yet to find discoveries. The discovered accumulations in any given area represent a sampling of the universe of accumulations, except that that sampling is skewed because as you have the first discoveries, they're likely to be the bigger ones, but it is a sampling. Thus, the FSD, the field size distribution, has to follow the distribution of the actual universe of accumulations. This is just statistics, including those yet to be discovered. This suggests that discovery sequence where larger accumulations tend to be discovered first introduces an ordering, but the sampling tells you what to expect. So then you go into exploratory process modeling tools, which are basically programs with algorithms that entail Monte Carlo simulations inside that perform probabilistic series of calculations on entry parameters to get stochastic results, and they do those things internally, and you don't see them, but basically you determine what the field size distribution of the exploratory area is. You estimate the number of possible accumulations, you quantify some geological parameter risks, you build a discovery sequence, and then you churn the numbers with all of these calculations, and you get an expected distribution and sequence of accumulations to be discovered. This is the output. And you do introduce a couple of concepts that have to be considered because you have a play level and you have a prospect level of risk, which is really uncertainty of geological parameters in the play. If you have a discovery, of course, it's all one. If you have a discovery, obviously there's a trap and seal and reservoir and all of this. The segment maybe not so, because within that play you have some uncertainties and you can quantify them. Inside this algorithm, it considers for the prospects these risk levels, and say in this case you come up with a 51.4% chance of a dry hole. That's low, but we're talking about the Presalt, and a 48.6 chance of success for the prospect, and you build that into the algorithm of the machine. It will, when you put in the information about the discoveries and the prospects you have, it will use that information. Basically, by applying Bayes' theorem, which describes behavior of conditional or marginal probabilities of random events, you first take the marginal probability, in this case of the play, if it exists, and if, like I said, if the play has a discovery, the marginal probability is 1. If there are no discoveries and you're still trying to model that area, you have to use multiplicative joint probability of geological parameters, so that if this is not all 1 because you don't have a discovery, you do have uncertainties regarding trap and seal and reservoir, and you apply all those, and you will get a probability for the existence of a play. the machine can do that for you. Then you do the same thing, probabilities for the prospect being assessed, and you multiply all those together. And you can also consider that there may be some dependency between those probabilities, and the machine can take that into consideration and do conditional probability calculations, basically following Bayes' theorem. It does all of this inside. This is what the algorithms are good for. You just have to put in the types of correlations and the percentages. And the wonderful thing is that's why we have those algorithms. The entry arguments are modeled by simulations, which basically are randomly sampled. They do follow probabilistic rules because you have to define the type of distribution, log normal, normal, skewed, that kind of thing. Limits or truncation. You have to define P90, P50, P10, confidence level of 90%, 50% is equally probable or most likely. P10 is a 10% confidence level, only 10% of the values will be bigger than that. For each of the parameters that you are studying for the prospect, thickness, probability of existence of the reservoir, migration, all of these things. For each individual simulation, you do all of these calculations, and the exit values are calculated deterministically. You just multiply each of those values one by one, and then you do that many times, and they are presented probabilistically. This is the concept that I will show graphically now, but you have to understand that this is why this works, even though you're not looking at each individual prospect from a geological analysis or looking at the geophysics or the seismic of it. Because you can study the by direct observations, that prospect, or you can use a representative model, which is this description, which is the chance of success based on geological parameters. And the Monte Carlo method basically substitutes the study of a deterministic process by a probabilistic model repeated many times. It requires a probability density to describe, the parameter. You need to generate random numbers. Very difficult to generate really random numbers. Basically, good pseudo-random numbers end up being okay, but you cannot generate series that repeat or known sequences. And you have to do this many thousands and thousands of times. And the precision depends on doing these simulations many times. So the machine, the modeling tool has to be capable of doing this. The USGS does this all over the world in many basins and using Monte Carlo simulation tools internally with their own algorithms. And they do this, basically, they do a random sampling of the distribution curve of the size distribution of the expected fields in a class, which is this distribution, for example. They randomly sample it, say they sample this one. They use that number to introduce into this distribution of the size of a certain class. And you take as many samples as this N here is. And for each one of those, you figure out how big those are. You add those up, size 1, 2, 3, 4, as many as N. And that is one simulation. You have one result. And if you repeat that 50,000 times, you have that one result and all the other results, which are sampled using the really random sampling. And you will get a probabilistic distribution of the total volume of expected accumulations. This is a not very smooth curve, even with, say, 50,000 repetitions. If you do 100,000, it probably ends up being a lot smoother. In our case, we didn't have at the time, say 2010, 11, 15, even more recently at the university, the computing power that the USGS has, but we did 5 and 10 and even more repetitions to get a reasonably smooth distribution output. So now you're able to output a yet to find result considering all those concepts, and you start gathering the information that you will use to input into this machine that uses these algorithms. At the time, it was GeoX, that was from GeoKnowledge. It was later acquired by Schlumberger, and I think they're trying to close it down or something. But there's many stochastic modeling systems and tools available, Monte Carlo simulations from many suppliers. This was a very good program because it did everything together, but basically it was just a tool to employ the concepts that we discussed. But the information that you have to gather from an area that you will study basically has to come from public sources, of course. In our cases, this was the ANP, Brazilian National Oil Body. They have a data bank with a lot of information from wells and discoveries and all of this. It's not complete and it's not all in one place, but it's about what we can get. And we also gathered information from all the declarations of discoveries from all the companies involved, basically Petrobras and others. Drilling, you get the well name, the location, lat long. You get the water depth just for situating the well. You get a date of well completion. Why is that important? Because we spoke that the discovery sequence is temporal. We need to know when. So the date is what gives us that when. And the result of the well, whether it was dry or not, and the expected volume at the time that the declaration of discovery is made. May not be entirely accurate, but it's a volume. So now and then you go back and can have a size of the discovered field. You do that on the map and see, the ring fence of the discovery area and so on. You put all of this information into all of the prospects and discoveries that were available at the time, for example, and they are called elements in this particular modeling tool. And you see we had plenty because the Presalt had plenty of prospects in being investigated at the time. Even though the assessment was in 2011, this was maybe about 2009 information or 2010 information. And it's basically the information from all of these blocks, wells, drilled, prospects for which there was significant information. And under those circumstances, you start plotting here ring fences and information about dates and all of this. All of that is put together in an organized fashion so that you can integrate that into the modeling tool to provide information on dates, sizes, and all of that. And then basically we came up with results that we went and published back in 2011. This was the first ever assessment of the yet to find oil potential in the Brazilian Presalt, which at the time was the biggest oil province in the exploration world. Probably, I think it still is. Attracted a lot of attention, maybe not as much in Brazil, but elsewhere. And basically, it used all of these screens that I can show you to show how we introduced the information that we had into the screens. For example, for elements of discovered accumulations, we actually had areas and information about reservoir thickness, geometric factor, all of these geological parameters to be able to input into the assessment tool with prospects and other segments for which we did not have all of that information. We could still put in estimates of oil in place or size of the accumulation and run all of these simulations to find a distribution of the possible sizes. Basically, that's what the tool does, Monte Carlo simulations with information from dry wells, because that tells you that it's still exhausted a certain area. Discoveries made, there were some, not many at the time. There was a lot of information about prospects. So you have to understand we were working from a very incomplete information of the exploratory area involved. And then we came up with results. We had a discovery sequence, not too many, not very smooth, with some major, more gas than oil, more oil than gas. It still shows that there's a very steep increase in the discoveries made according to the efforts in new wells drilled. That is a very important result because that tells you that the discovery sequence is still going up steeply. We also found a field size distribution. Not surprisingly, it lies along a straight line more or less. And these are, say, the discoveries that were known. Obviously, along these lines, there are likely to be many others that are the yet to find discoveries. The machine does that. And when we start inputting the number of the distribution of expected number of additional fields, it comes up with all of these probabilistic results. Say for a 90% confidence level, it expects at least 42.5 new accumulations, say 42. For a 10% confidence level, it expects 83 new accumulations. So this is the output from the extrapolation of those field size distribution and discovery sequence that we inputted. The same thing for the size of the accumulations. With a 90% confidence level, at that time we expected at least 165 million recoverable barrels. We worked on recoverable basis by using in-place times recovery factor. So these are actually recoverable oil and gas numbers. 90% confidence level, at least 165 million, 10% confidence level, almost 8 billion. And that's more or less what was the case. We had Lula around 8 billion barrels or more. So this modeling simulation basically provided results that were entirely within what we were finding. The total resources to be discovered, the same thing. 90% confidence level that it would be at least 114 billion barrels, and 10% confidence level tells us that it's only 10%. The accumulations are 288 billion barrels, only 10% chance of there being more than that. So we have now, say, a spread of 114 to 288 billion barrels of recoverable resources. At the time, no one was talking about these numbers. Obviously, very different numbers on the low and the high side, but we had very high levels of uncertainty. So this is what we could come up with in the modeling results. But they were much higher than anybody else was talking about, and maybe for that reason, a lot of people doubted some of those numbers. But for that same reason, after a couple of years, there were a lot more wells drilled. Petrobras was drilling like crazy, even some other companies, and there was a lot more information available. Come 2015, Professor Hernani Chavez and I again published a reassessment. So now this time, we have a lot more fields discovered, a lot more information on prospects. So now we can do the same type of modeling with a lot more segments to be inputted, information much more recent, a lot more information, and you basically go through the same thing. You can add correlations to the probabilities. We still have about 48% chance of a dry hole. This is, for the pre-salt, a very conservative number, because the pre-salt at that time people were saying, it's almost guaranteed you'll find something. Okay, in our assessments, we were being realistic. Obviously not 100% success. And we introduced some of these uncertainty factors for things like reservoir presence and so on. But of course, the play was one. There were a lot of discoveries there, so we know that there was a functioning petroleum system. The individual segments that were well known were assessed through direct estimation of volumes and simulation of those segments. Individual ones included dry holes. So for a dry hole, the play chance is 1, but the modeling for that dry hole and for other prospects that might be a dry hole would have to show 0. We don't know if it's all zeros, but the result has to be 0. So we did include dry holes in the assessment. We included assessment for fields at that time that were still not very well assessed, but we came up with big numbers and a big spread because there was a lot of uncertainty. For Libra, also big numbers. For many other prospects that were not well assessed yet, we included information that allowed the prospect assessment to be modeled. And then for those prospects where we introduced uncertainties for geological parameters, we used those uncertainties. For gas and fluids, we used different probabilistic distributions of the expected, say, gas-oil ratio, recovery factors for associated gas, oil, the gas fraction, condensate yield, all of these things. We describe probabilistically. The machine defines a probability curve from which are sampled those n's that we discussed before. In the Presalt, there's also up in the north a whole region which we call a subplay called Parque das Baleias, which has many discovered fields in the post-salt, but they actually have pre-salt plays also. And so we modeled all of those individual prospects there under the post-salt, and then we counted them all up in numbers, size, and total volume, and we included excuse me, we included all of that as one segment in the pre-salt play assessment. But it was a big segment because something like 3.8 to 6.8 billion barrels of expected total recoverable volumes in the Parque das Baleias play in the north of the pre-salt. And then we did assessments of all of those segments that might be significant. We did it for the transfer of rights area and many fields like Búzios, for example, oil, associated gas, non-associated gas, condensate. The results can be presented in many ways. This is just to show you that if you want to get into it, there was a lot of analysis available. Basically, we came up with 90% confidence level that it's above 5 billion up to 7.9 billion, which for Carcará is entirely reasonable. Same thing for Carioca and Jupiter, which was a lot of gas. So the BOE is basically considering mostly gas, as you might see here, a lot, some oil, but a lot of associated and non-associated gas and condensates. This was well reflected, of course. Libra also, in case of Libra, we showed first in place volumes because there was a significant uncertainty about the recovery volumes, given the fact that the contract was for 35 years and maybe not all of it would be recovered in that period. And also we didn't have a very good idea of whether all the FPSOs required could be put in place and so on. So we had a very high uncertainty in place, and then you can just apply the recovery factor to obtain recoverable. We did that for Lula, similar things in place, assessments, oil, mostly oil in this case, but Lula and many other of the pre-salt fields, especially these big ones, have a lot of gas, and this is what we see here. The information reflects the fact that the geological parameters introduced in the assessment show that there's a high gas-oil ratio. That is just churned out in the results, which is intuitive, but it seems amazing to some. And then we did an assessment with some conditions, maybe limiting overall maximum field size at 20 billion barrels. You know, it's pre-salt, very positive, but let's put a reasonable number. You can't expect 30 billion, but in fact, we're getting close. Now we're talking about fields with 10, 15 billion barrels. We do the definitions with discoveries, segments, including prospects and so on. We put definitions as to number of the postulated plays, the discovered resources up to this point. So they are counted as discovered resources, the play chance, and we get results. A new discovery sequence, which is more populated than the other one. There's other points here. But it's still increasing, so we don't see much flattening. Obviously, we don't expect to. The other one was not very different, but at these very early stages, you can't expect much difference from 2010 to 2015. Still a straight line along a field size distribution curve on which future discoveries will lie. The other field size distribution curve a little bit different, but still not very different. And then we get, you know, the risk summary. We said 49% segment play chance. We had a 20 million barrel threshold for a minimum accumulation to be counted. It's small, but we're talking about the entire history of exploration of the pre-salt, which might be 30, 40, 50 years. So in 50 years, maybe a 20 million barrel accumulation could be something that you might want to count. So probabilistically and in stochastic assessment, you can't ignore some sizes, even if they seem small nowadays. Same thing for discovered. And then we plot these. Number of accumulations, 75 to 102. And the number of yet to find accumulations. This is the number of accumulations we expect that there exists in the pre-salt. This is the number yet to be discovered, because we already have lots of discoveries. Back in 2015, we had less. The size of individual accumulations, 245 million to 6.5 billion. Naturally, we have more information. So the yet to find size of the individual fields, 239 to 5.9. Back in 2015, it was 165 to 799. The spread was bigger. Now we have more information. We're narrowing down the results, which is very good. It shows that the tool is behaving, the modeling is behaving as we would expect as we have more information available. Total recoverable resources, now we're estimated 175 to 273. This magical spread is the number that has been spread all over the world when people talk about the pre-salt. This is total recoverable resources that we expect exist in the pre-salt above minimum threshold. Back in 2015, we had yet to find, that was 114 to 288. Now we have 118 to 216. Again, narrowing the yet to find numbers. But now we get to 2016, low oil prices, maybe not as low as now, but is very opportune that we have a situation such as now where people are saying, well, with the oil prices in $20 and $30 range, of course, I'm not saying $10, but 20, 30, maybe those areas won't be viable economically. So the study we did then is very pertinent now, because we looked at what would happen in a very low oil price, lower for longer scenario. And we concluded that the numbers back in 15 were reasonable, even though they were large. And the methodology was robust. We saw the narrowing of the results, but it was reasonable to try to redo things to adjust for a lower oil price scenario. So we introduced a very much higher minimum threshold, which statistically doesn't make a lot of sense, but we have to be very much more conservative with the low oil price and say if it's going to remain low forever, we're just not going to look for some accumulations much below that. And we reduced the recovery factor, and we did some other changes that made the process more robust. We put here 100 million barrel minimums and reduce the recovery factors for everything, for oil, for gas, associated everything. The probability is now still high because the pre-salt has those numbers. You have to remember that everybody that works in the pre-salt swears that you know, it's almost a guaranteed ticket, which we know it isn't, but you know, that's why these numbers look very much better than they might be, for example, even in the Gulf of Mexico. And we get results, same overall assessments of recoverable resources, the lower for longer number of yet to find accumulations, 49 to 77. Well, back in 2015, there were 56 to 83. So now maybe a few less. The size of the accumulations, 423 to 6.7, you know, still very significant sizes. Back in 2015, the values were spread out. They are bigger though, but this is what might catch some people. The lower for longer assessment also in the yet to find oil recovery is 130 to 233 billion barrels. And back in 2015, it was 119 to 217. But even though this is higher, it is because we have discovered resources in the lower for longer scenario are much lower. What people discovered and they thought would be very big, now we're assessing down those discoveries. And back in 2015, we were assessing them up to 51 to 61 billion barrels. So that is why now the assessment is 130 to 233 total yet to find recoverable resources. Still very significant, and it tells us that we're looking at a very viable province. In 2015, we had this magical number, now lower, of course, of the total discovered and undiscovered. And we have something that we had shown before. This is what we call a rosy future diagram, just because we haven't painted rosy. Forget the scale, but it's basically showing you that from this point onwards into the discovery sequence, we will have more discoveries until we get to, say, the 193 billion barrels total. This is what you would expect from now until the end of the exploratory history of the pre-salt. So this is what we have to look ahead for. Indeed, despite all the adjustments and so on, the numbers are basically 11% less for the total recoverable volumes. And the results basically put to rest this thing that the pre-salt might not be viable with low oil prices. And we're looking at wells producing 60,000 barrels a day, Petrobras claiming $5 to $6 a barrel lifting costs. Obviously, the pre-salt can withstand these low oil prices. And given those prices, we can do an assessment that shows that there's a lot of barrels to be discovered there. Even in this scenario, total recoverable yet to find volumes are very large and still distributed, not just among one or two large discoveries, but among many discoveries. But this puts forth a very important point. Brazil faces a major challenge of producing all that recoverable oil before the end of the oil age. This is what I say is the context in which we have to look at these results. If the end of the oil age were to very conservatively occur by the end of the century, say 2100, Brazil would have to produce an average of 5 to 9 million barrels, depending on the P90 or P10 levels, a day until then. This is, Brazil's producing 3, say, this is an average that has to last for the next 80 some years. And even more if we're going to produce the oil that's in the post-salt and in the other basins in Brazil. So if we consider that the oil age may actually end much sooner, as we're discussing nowadays, then these average production numbers have to be much higher. Brazil basically will have to go to 10 to 15 million barrels a day to be able to produce all of this oil, or it will remain in the ground after the end of the oil age when it just won't be demanded. This is a major challenge. This is the point for discussion for many of the geopolitical forums in which I'm active. I put together this if we want to discuss, but basically we can see what happens with the numbers of the 2015 and 2016 assessments as low oil prices are considered. You know, the total recoverable accumulations obviously less, unrisked size of accumulations end up being higher because now you're not looking at smaller accumulations. And if you're just focusing on larger, more economical or viable accumulations, this is what would be expected. And this is what's shown. And this is a good topic for discussion, more in-depth discussion. Basically, more topics for discussion. This is what I had to show. I think that it's enough to provide forum for questions on the theory and on the results. So basically now I leave it up to you, Mauricio, to guide some questions if we have any, or to let me know where we go from here.
Okay, Professor, thank you very much. Excellent presentation. So from this moment, we will start for the questions and answers round. We have some questions in the Q&A. So Professor, you can read and answer that questions, okay?
Wait a second, I don't see it. Let me see that.
And the bottom of the screen,
yeah, I'm trying
the
to
Q&A.
Yeah. Oh, yeah, let's see, what do we got here? Oh, Azure, nice to, okay. How the price of oil, gas, and mineral discoveries. I assume that many discoveries with lower volumes will be considered dry or non-commercial. Exactly. Can we take oil gas prices risk factor in addition to the geological risk? Okay, let's talk about low oil prices and lower oil prices. We have very low oil prices now. At these current oil prices, I suppose that we could very well say that they are a risk factor in themselves in terms of viability for certain companies and so on, which might throw the geological expectations of a pre-salt region into question just because the companies might not be viable themselves. But we're looking at the pre-salt as an assessment area, and we're saying, what does the pre-salt hold for the future, even if oil prices remain very low? Very low is a relative value, a relative concept. So very low means that from the levels that we were talking before, 40, 50, 60 or more, we cut those numbers, say, in half, down to 20s and 30s. If we see that the operators in the pre-salt tell us, as they do, that their break-evens are now 25, and we can still expect technology to continue to work, and we can still expect all of the assessments to remain correct in geological parameters, all we have to do is reduce, say, the recovery factor and reduce and increase the size of the minimums to take that into account. And in fact, you have to consider that recovery factors are very conservatively estimated even nowadays. We talk about 25, 30%, 20 to 30%, many 25%. For these major fields, that is very low. You have to remember, in 20, 30 years, or however long it takes to exhaust some of these fields, technology will evolve so that maybe we can move up in the recovery factor, just as we're seeing in the North Sea and many other areas, even in the Santos and Campos Basin. We now have fields that are looking at 50 and 60% recovery factors. So to say that pre-salt fields that are extremely prolific and very large and so on are only going to achieve a 25 or 30% recovery factor is actually putting a very conservative assessment onto them. And this is why I think that we can, whatever additional risk factor we want to place on these assessments, I would say that on the other hand, the recovery factors are the things that are being much underestimated at the moment. So I think that all of these numbers that we presented, if they're just an assessment, probabilistic, but if they were to be questioned on one side because they might have to be more conservative here and there, on the other hand, they also can be, it can also be argued that they might be more favorable over the next 15, 20 years, even if prices remain at equivalent, $20, $30 or whatever. But that's my view. And then the other question was this question about Monte Carlo method. Monte Carlo simulations are a whole theme apart, and there's a lot of information about this. The ideal way to treat this is go look at statistics and simulations and so on, and then you see how the Monte Carlo method might work. But these tools, these assessment tools, basically introduce that the Monte Carlo method inside with algorithms that do what I showed in those in the USGS slide that basically all systems do. They sample and they calculate and they store that number, they sample and they calculate, store that number, then look at the 50,000 results and build a probability curve. And that is a very robust assessment method because you're doing this many times on information that you input it, on the expectation that the parameter works like you estimated. Say reservoir thickness is a normal distribution between 10 and 40 meters. If that's correct, then the assessment of the prospect and then of the total will also be robust. If your geological information is not correct, obviously. That's why we have this big distribution, wide distribution in input numbers, the minimums and the maximums. Let's see. Mauricio, do you have a favorite question or can I look through some here? I see
no, Professor, you can continue with the questions.
All right. I see that discovery of oil and gas in the near and far future. This assessment, this is something that I may not have made clear. This assessment of the pre-salt, like we've done many assessments of the Sergipe-Alagoas Basin and Campos Basin and elsewhere. These assessments are of a geological basin or province, a region, and they are not temporal. This is the total basin being assessed has these accumulations of this size, these number of accumulations for which the total is that. This means that over the next X years, the number of wells drilled will eventually discover all of these accumulations. That may take 10 years if you're a very aggressive driller, or it may take 50 years if you take it easy. It does not matter. The discoveries yet to be made depend on the number of wells drilled, not on time. So this is what will be discovered as long as the oil age is there and oil prices are not zero or negative. So it does not have a temporal estimate or prediction to it. The only temporal prediction involved is a relative one. This is the discovery sequence where it shows that the bigger discoveries are likely to be found first, and the sequence will be this. When that sequence is achieved is not by year, it's by the number of wells drilled, which may be all in a very short period or a very extended period. So this is a very important concept to keep in mind because we don't talk about years, but we talk about number of wells drilled. Potential accumulations, about 100 million barrels will possibly never be drilled in the pre-salt. Why not shift the volume counting threshold to a couple 100 million barrels and above? Okay, that is a reasonable question. Why take 100 million barrels? Why don't we go to 400 million barrels, say? Right now, in the pre-salt, no one is looking for accumulations under 500 million barrels, I suppose, recoverable barrels. That is today, 2020. In the next couple of years, as you have more infrastructure in place, if you have another discovery next to Buzios, and it's only 50 million barrels, and it only takes 5 kilometers of lines to hook up, why not hook it up? It will be a discovery that will be economical. So to artificially raise the threshold to levels that are over the time of life of the play is not very useful, because that cuts out the fundamental assessment, which is not temporal. You're trying to put into a 2020 assessment of what viable is, whereas we're looking at the history that might be developed for the pre-salt in the next 30 years or so, or more, very likely. If that 30 years happens, if the well age doesn't end beforehand or anything like that, then at that time, it will be just like in the North Sea. They're looking at a couple million barrels here and there. You know, you will be tapping the smaller accumulations because they will be viable. They will be economically, they will make economical sense, even if they're not 400 million barrels or 100 million barrels. So we cannot artificially increase the minimum to a point where over the lifetime of the exploratory history, that would not make sense. It is something difficult to accept, but you know, today obviously no one will go for a prospect that's not significant unless it happens to be right next door to another one, and we're beginning to see that. So even in the pre-salt, the lines and the production lines of the equipment is going to make that assessment consideration reasonable. There's another question here. Did we calibrate the discovered volumes and the yet find volumes with the volume of oil potentially generated and expelled by the source? No. As I mentioned before, if you have a basin that is very well known, explored, seismic was done everywhere, you have lots of wells drilled, and you know everything about the basin, you could very well do an assessment of the basin. All the oil that was produced, you can figure out the volume of the source rock, how much was there, how much was expelled, how much was lost, and you come up with a value of the oil that went into reservoirs and what's still left. It's basically a volumetric original value minus produced, and you get to find. This requires a very well-known assessment area. The pre-salt, as you can see, is still in its infancy. We're doing these assessments with a high level of uncertainty, and that's why we get, you know, P90 and P10s very different, because we still have a lot of uncertainty, but it's somewhere within that range, which is very big, tells us that we cannot yet do a very deterministic volumetric assessment, because we don't yet have enough information about the pre-salt trend to do all of this. So later, as we are getting to the point now in very mature basins, we might do that. Right now, we're not doing that calculation. Individual fields and prospects might be able to do that. If you have very good information, you do 3D seismic, you understand very well the source rock and the reservoir and all the migration paths, and for that small area, you understand all the geochemistry involved in losses and so on, you might be able to do that kind of volumetric assessment, and you might get very good information. But we're talking about an assessment of 150,000 square kilometers. So no, we're not doing deterministic assessment for this basin. And this is the basis for doing some kind of an assessment where it might have been impossible otherwise. Remember, in 2000 8 or 9. Brazil was saying, oh, the pre-salt is a wonderful thing. And the government here was saying that this is a lottery ticket that's a winning lottery ticket even before we check it. Well, obviously there was a lot of optimism, but no one knew numbers exactly. And even some government figures were saying, we might have 80 billion or 100 billion barrels. Where'd they get those numbers from? There was no assessment method possible. They had, Lula was a discovery, basically. So we started looking at all of this exactly because there wasn't a methodology that was applied to the pre-salt to be able to say what to expect. And we provided a very uncertain assessment, 114 to 200 to 300 and some, and then we narrowed it down. Finally, we narrowed it down to from 170 to 270 billion barrels. Still a wide range, but now we're narrowing down the assessment of the resources that are recoverable in that basin. As time goes by, if we do this 5-10 years from now, we will be able to narrow this much more. It has already been shown that this tool is very robust, and we get the results that we expect, which is narrowing, increasing of the P90 and decreasing of the P10, because we're finally narrowing down on the actual value that is recoverable and will be produced in 30 years. At the end of the exploratory history of the pre-salt, we will have an exact number. We got 180 billion barrels out, that's it. But that is only at the end. Until then, we will do all of these calculations and narrow our uncertainty as time goes on. But it is important that we were able to show that the tool and the methodology behaved as we would have expected for a robust methodology. And if we start considering exogenous factors, such as very much lower oil prices that affect recovery factors and minimum sizes, we can adjust those, and the numbers we get back are also reasonable in accordance with the adjustments we made. So the minimum sizes and the recovery factors, I think, have been reasonably considered. I would say that because many people still argue that, well, you can't talk about over 30% recovery factor because we didn't get that. Yes, we didn't get it today in any of these fields, but we might exceed that by a lot in 10 years, because then we will come with enhanced oil recovery methods that might very well be worthwhile in a field like Libra or Buzios or Lula or anything else, because at that time the technology will be worthwhile. As Mauricio said, I mean, I did a lot of work in microbial oil recovery, enhanced oil recovery, and even though that is not really a big thing for some of the pre-salt oil fields nowadays, there are many proposals out there, including some of ours with professors from University of Bahia, Federal University of Bahia, where we are talking about recovering gas and oil from some of these pre-salt fields that have high CO2, for example, and be able to use enhanced oil recovery, microbial and enhanced oil recovery, to increase recovery factors from fields that are now considered problem fields. Jupiter is one. You saw the assessment that we showed, a lot of gas, not so much oil. Originally people were excited because it was very big, and then people got disenchanted because there was a lot of gas and a lot of CO2. Now maybe it's possible to envision a future in which that recovery might be very much enhanced with some methods that are not exactly viable now, but may come to be so later. So technology is the key. And I showed some of those changes in the discovery sequence that can happen in the pre-salt as well. Obviously, technology is improving in terms of drilling speed and costs and days involved and all that, but I'm talking about fundamental changes. One day we get a means of putting everything on sea bottom and costs drop by half or whatever, that will make a difference. And it's very important to know that over time, production costs, operating costs, and so on can lead to increased recovery factors, which that is the reason why we considered in the spread of the recovery factors considered, we put as little as 15%, maybe as high as 40%. Obviously, not very much chance that it will be 40, and maybe not a high chance that it'll be 15, but that gives you a range, and it is possible we could get to the high end. CO2 risk. I just spoke a little bit about that, but if CO2 is above a certain threshold, discoveries may become technically and economically not viable. That is exactly what I was talking about, enhanced oil recovery methods that might make recovery factors go up significantly in the future. In fact, if you talk to all of these companies, they do have, almost all of them have some kind of program to reach high recovery factors in their operated fields in the future. They're working now maybe with 30% recovery factor with the equipment they have, the technology they have, but if these fields are going to be producing for 20 years, certainly 5, 10, 15 years from now, the technology may be applied to make these fields either produce more or produce less expensively and enhance oil recovery. And in my case, of course, I always make a plug for microbial enhanced oil recovery. Might make a big difference. And it's exactly in the high CO2 fields where we might see that. Those are huge fields. We're talking 8 to 15 billion barrels equivalent, and mostly gas, and a lot of CO2, which is obviously doesn't count. It's not energy and doesn't contain energy. But if we can turn some of that CO2 into methane, and microbes do that. They do that in place. They do that inside the reservoirs. They can do that. They can consume some oil in doing that. But if you lose if you lose a barrel of oil to produce 10 million cubic meters of gas, that's a good trade-off. And if you can make that field do that in the future, you will all of a sudden go from an uneconomic field to a very economic field. It just depends on technology, and technology in high CO2 fields is very important in the pre-salt because we do have a lot of fields with high CO2 levels, some that indeed today might make them uneconomical or not as attractive to develop right now. Put it in the back burner, maybe 5 years from now when we know how to do separation or something, we'll develop them. In 10 years, instead of separation, we might do conversion of CO2 to methane. So this is technology. We don't explicitly consider it. We consider it in the input variables that we use for recovery factor. And that's why we consider that some of these prospects and discoveries could have recovery factors as high as 50% in some cases. Very small chance we put, but it is possible. And in 10, 15 years, we might see that. Then we also have, apart from the basic geological parameters, you consider elements, migration pathways, synchronism. Yes. What happens is when we talk about uncertainties from a geological point of view, we have play uncertainty level and prospect level uncertainty. The play uncertainty level, we've basically said, is not uncertain. We have a working, very prolific petroleum system. The geological uncertainties apply to prospects and even some discoveries, such as the rocks that are going to hold the oil, the reservoir rocks, and also the migration paths to that. Each of those geological parameters has a specific uncertainty level. If you're still looking at this, I don't know if I can go back and show some of this, because some of these, well, this is for the play, but now let me show you one for the, we explicitly considered reservoir presence, reservoir effectiveness, source presence, source effectiveness, trap presence, trap effectiveness. The migration is built into the effectiveness of reservoir and the presence of the reservoir. So one way or another, the petroleum system uncertainty that applies to that prospect was indeed modeled in all of the geological aspects that would apply to that prospect. We can argue whether the uncertainties that we applied are more or less, but remember, we're talking about the pre-salt, which unquestionably is an exceptional play. If we were to be doing this in the post-salt, elsewhere in the Campos Basin, for example, we would have used much lower certainty or much higher uncertainty levels for those parameters, because the geological uncertainties would be much higher. But they are all, yes, explicitly modeled, and for each parameter, we sample that uncertainty many times. So the simulations do this thousands of times using those uncertainty percentages for each of those risk factors. Is it possible to assess yet to find hydrocarbon from the prospect that never been drilled? Yes, we did that. Some of those prospects that were assessed were not drilled. They're just prospects that were identified on seismic, for example. And of course, seismic is pretty good nowadays and all this, but you know, you still have to drill to find things. And Petrobras says that pretty soon they will be able to declare discoveries without drilling. But in any case, we have many prospects that were assessed just because they were in a block that ANP or Petrobras or someone said, this is an assessment unit that we're considering to drill sometime. They've obviously looked at the expected thickness of the reservoir, the extent, the characteristics. They've done some studies. If they have analogs, they've done some studies on what the likely permeporosity parameters are, the oil saturations, all of these things, which we explicitly modeled also inside. These are all detailed, but they're in there. And they came up with a probability curve for the behavior, for example, of the existence of the thickness of that reservoir. And we modeled it. And we said, well, this prospect, which has never been drilled, and we've identified it in seismic, and even though seismic is good, we're saying that the reservoir thickness is not 40.5 meters. It's somewhere between 30 and 60, say. And the chances of it being somewhere there are described by a certain probabilistic curve that we also insert. And it's a triangular distribution, it's a constant distribution, it's a normal distribution. As geologists, we input those numbers based on our knowledge. It's questionable if others might do the same, but we did that, and in agreement with obviously the consensus of the industry, basically. But for most of these parameters, we describe the probability distribution for this geological parameter. For example, thickness. In other cases, it was geometric factor or the extent of the area that the prospect involves. So eventually, if it's going to turn into a discovery, we say it is, you know, X kilometers in extent. Well, that's also an uncertainty. It might be 100, it might be 200. Very likely to be over 100 and almost not likely to be over 200. But somewhere in between, we have to describe the behavior of that geological parameter, and we do so. We put limits, we describe probabilistically the probability curve that describes that parameter, and the assessment tool does Monte Carlo simulations on that probability curve. So it's all explicitly considered. And it is, of course, deterministically calculated each time, and of course the simulation many thousands of times. So we get a probabilistic result that does take those parameters into consideration. I think we're running out of time. Let's see what else we have here. Why did we use Monte Carlo method instead of what? If you're going to do an assessment of a basin that you don't have a lot of information on still, and this is a very immature basin still, you basically have to do an analysis, like we said, an assessment analysis that is going to rely on a stochastic assessment of parameters that you develop from the few points of information that you do have. The points are the discoveries, the prospects, information you have about each, information about the geological parameters of each one, and so on. In the Presalt, we have those, and we did a simulation based on those items of information. In 2008, 9, 10, that was not a lot of information, so we had a lot of uncertainty. In 2015, it was a lot more, 2016 more. So the uncertainty is always going to be there, and we don't have complete information, so we do have to model with one of these tools. And the only way to actually sample all of these individually and build a result that is probabilistic is with a Monte Carlo type method, where you're sampling, producing a value, sampling again, and then analyzing those values. And until we get to the point where we can do a direct estimation, analyzing each and every prospect and so on in the Presalt trend, we can do anything but an assessment of this type. This is what the whole point is, an assessment of the Presalt using a modeling tool of the exploration process itself. And it is statistically based. Mauricio, we're basically out of time. Do you want to say something?
Yes. No, Professor. So we end with the questions and answers